Hello. So let's start. So is this slide visible? Hello, students. Can you able to see the slide? Hello.
Yes, yes.
Yeah, good. So, so the next topic we are going to discuss is the process scheduling. So you see that we are discussing about the process. Initially, yeah, at the beginning we discussed about the concept of a process, then various aspects of a process where there are various states of a process, right? And afterwards, very briefly, we discussed about how to schedule the process and all, very briefly, like a short term, long term schedulers and all, right? And after that, we discussed about how the process will communicate among themselves, right? Using shared memory and like using a mailboxes or like message communication, right? So those aspects we discussed, and afterwards, uh, concept of threads we discussed, right? The process and threads, both of them are the execution units only. But in the context of process, we assume that the process contains a single thread of execution. And for effective utilization and for effectively for effective computation, a process can be run using a multiple threads, right, in a multi-threaded environment. And so in that context, we discussed about threads, right, and various aspects of threads, like how the threads can be created and how the threads will be, the concept of threading, how it will be implemented, right? How the threads are created, controlled. So, and the examples of the operating systems, how the threads are implemented. So those things we have discussed. And the next topic that we are going to discuss is the process scheduling. Today and the next lecture, we'll try to cover these things. And afterwards, we discuss about the process synchronization, right? So that means when your process are execution under execution, they may have certain dependencies. Suppose some process or some number of process, they are computing, they are somehow computing on some data, shared data and all. So in that case, how the process should coordinate and should synchronize so that there should not be any errors arise due to the access of the shared data by multiple processes and all. So that we'll discuss later on after this topic and all, right? Then we move on to the memory management and so on, right? Okay, so coming to the process scheduling, so this is basically is very uh, like very intuitive. Like most of the things that we are going to discuss will be very simple and very intuitive, very generic and intuitive. And day-to-day life, most of the times we experience these things uh, like we have multiple tasks, and then how do we carry out that? Like the way you schedule that depending upon the urgency or depending on the need and all. So the similar things also here we are using in the context of scheduling the process. And yeah, these are the various things that we are going to discuss, the basic concepts like the scheduling criteria, like how, what is the criteria in scheduling the process and all. Like when you're giving the access to the CPU, on what basis you are giving, you are choosing a particular process for giving execution to the CPU and all, on what basis and all. So that's a criteria. And what are the various scheduling algorithms, right? And then the thread scheduling, very, very briefly, we'll discuss about what is, how the thread scheduling will be done and what are the various points or various things that are arise in case of thread scheduling. And a multi-processor scheduling, suppose we have, like, as we know that most of the systems right now are the multi-processor systems or multi-core systems and all. So in that case, how the processors are scheduled, right? And then there are other things and all. So if time permits, we'll go through these things, other aspects, like what are the operating system, like in a realistic operating systems like Windows and this Mac OS and other Unix systems and all. So how the, what are the scheduling algorithms that are it will be there. and first of all, how these scheduling algorithms are evaluated and all, right? So these are the various things. So among them, we'll see that whatever we can cover in these two lectures will wind up till that point. Okay. Then coming to the broader objectives of the process scheduling. So here the process scheduling, we try to focus mostly on the prime resource or the very crucial resource among the various resources that are available in the computer. It's a CPU. So here the process scheduling is nothing but mostly we focus on the CPU scheduling. Otherwise, the process scheduling has to be done at every resource, right? At the CPU or at the IO devices and various other resources also. But here in this context here, we try to focus on the process scheduling means how the processes are scheduled to the CPU's execution and all. You can sometimes you can call it as CPU scheduling also because the CPU will be scheduled to the various processes and all to support a multi-programming or multitasking and all, right? So the CPU scheduling will introduce that in the context of multi-programmed operating systems and all, and describe the various CPU scheduling algorithms. We'll see that, and then we'll discuss the evaluation criteria, like on which parameters are used to evaluate these scheduling algorithms. And finally, we'll see that how these scheduling algorithms will be supported by the operating systems and all. And then when you are looking at a system, a process, for example, and its execution, you can basically see that the process execution will be an alternative way of CPU burst and IO burst. Here the burst means actually the sequence of instructions. So that needs the execution for its execution, it requires the CPU and all. And IO burst means for this particular sequence of instructions where the CPU is not required, where it requires the devices, IO devices and all. So that way, when you look at the sequence of code, a sequence of instructions in a program, you can see that you can see the a CPU burst followed by the IO burst, and again once the IO is completed, and again the CPU burst will be there, some computation, and afterwards again some IO will be required. So when you look at the process, like the structure of a process, so it will be like you can see that alternatively like a CPU burst, IO burst, CPU IO burst will be there alternatively they present and all, right? And when you try to look at the the CPU burst, you can say that the histogram of CPU burst times, when you analyze that, you can able to see that suppose a program is there, and then when you look at when you try to execute that program for certain amount of time, some sequence of instructions it uses the CPU, and afterwards it requires IO, and in that where it needs with the help of operating system code or whatever, it performs the IO, and again it will come back to for CPU execution, then again some other thing. So likewise, when you analyze these the CPU burst means actually here it's a contiguous time in which the process is using the CPU and all. It's a contiguous time interval in which the process is continuously using the CPU, right? So that way, if you analyze the CPU burst durations or in a process or a group of process, so it something appears like this. You can say that there are lots of CPU bursts having a smaller durations, and very few CPU bursts having the larger duration and all, having the slightly larger duration. If you look at here in terms of milliseconds and all, you see that like most of the CPU bursts the more number of CPU bursts having the lesser duration. That means less than 5 milliseconds and all. And there are few CPU bursts. You can see that there are a few CPU bursts. Their duration is a bit longer and all, bit longer. Then coming to the CPU scheduler is nothing but we have a CPU. It's a very important resource in a system, and where if you can optimize the CPU, that means if you make sure that, or if you try to use the CPU like the most of the time. That means we have to keep the CPU to be busy all the time by executing the various processes and all. Then automatically the efficiency of the system and lots of other parameters will be improved. Like it means that one thing is the throughput will be improved. Like we can say that lots of programs will be utilized or will be executed and all in a given amount of time, right? And you can able to see a progress in the multiple programs, several programs and all. So for all these things, the crucial resource that need to be optimized will be the CPU and all. CPU. And so the CPU scheduler, nothing but actually here, it schedules the process and then it will give the process one after another to the CPU so that the CPU will be busy or CPU will execute one or other process at any point of time. And while these processes are scheduled, when the processes are maintained, the queue by the appropriate by a particular scheduler and all. And there are various ways of ordering the queues, as I mentioned. We'll see that in the later part. We'll basically discuss about that. And the CPU switching decisions can take place in the following four ways, the four possibilities. Sometimes the CPU switch from running state to waiting state. It means that a process is running, and at some point of a time, the CPU or the process state will be changing from running to waiting state, right? It means that till that point, the process is running, process is executed by CPU, and at some point, the process will be coming out of the CPU and it will go into the wait state. It will go into wait state. So the reason for going to waiting state will be different. That means the process may need the IO, then it may be waiting for IO from a keyboard, or it may be waiting for IO from a file, or it may be waiting for, like for example, a processor created a child process, then afterwards it may be waiting for a child to complete. So likewise, there are different reasons for the waiting state. A process may go into the wait state and all. So at that time, when a process is moving from running state to the wait state, it means that this particular process voluntarily it is moving out of the CPU, moving out of the CPU. So therefore, we need to give some other process to the CPU for its execution, right? So this is like one way where the process is voluntarily moving out of the CPU because it has to wait some event to happen, right? That means some input to be taken or some signal to be arrived or something has to happen. And another thing is the switches from running state to ready state. So this will happen. That means the process is running, and then immediately the process will be move on to the ready state. It means that the process will be taken out from the CPU, and it will be again kept in the ready queue, ready state. Ready state means ready queue. It means that the process is now running, and now it will be taken out and again placed into the ready queue. So this is nothing but you are forcefully taken out of a process from the CPU, and again we are placing in the ready queue because the ready queue means the process is want to execute, want to perform computation, right? And now it is in the computation, and it is taken out of that, and again we are placing in the ready state. It means that it requires the CPU again. So here it means that the process sometimes the process switches from running state to ready state. This will happen due to some interrupt. This will happen due to some interrupt. The interrupt may be the timer interrupt, or the interrupt may be with some other like external interrupt or internal or some other interrupt and all, right? So because of that, the process right now it's execution, and then it will be moving from it will be leaving the CPU forcefully, and then it will be placed into the ready queue. And this is nothing but this is not voluntarily the process is leaving the CPU. Here the process is forcefully leaving, forcefully switching from the CPU to some other state, from running state to the ready state and all. And another thing is that actually there may be switching, CPU switching may be required where a process, something like a process switching from waiting state to ready state. It means that actually suppose a process is waiting for something and then the event has occurred and afterward the process is now ready for execution. So there also when the process is moving from ready to waiting to the ready state, so there also a process CPU switch may occur. We'll see that why when it occurs and all, right? When it occurs. And finally a process terminates. So when a process terminates means the process reaches to a last statement. There is no other instruction to execute. That means process reaches to a natural termination. So when the process is reaches to natural termination, then there is no other instruction or no other to be run by the CPU. So therefore the process terminates. So therefore the CPU is idle. CPU is now ready to execute some other process and all. Right? So there are the four cases where the CPU scheduling decision has to be made. First one is that when the process is moving from running to waiting state, it means that the process is voluntarily leaving from the CPU. At that time, now the CPU is free. So therefore, the CPU scheduler has to take a decision. Which process has to be given next and all. Which process has to be given next. And then the last one is the fourth one event is that when a process is leaving natural termination, when a process reaches to a last point and there is nothing to execute, that is the completion, that is the last end statement and all. So therefore, the process is leaving the CPU, again here also voluntarily. So therefore, a new process is required to execute. So here, out of these four cases, the case one and case four are these one and four cases where the scheduling is going to be non-preemptive scheduling. Non-preemptive scheduling. It means that during these cases where the process is voluntarily leaving the CPU, so therefore the CPU has to be scheduled a new process. So this is known to be non-preemptive scheduling and all. Non-preemptive scheduling. Whereas other two cases, no, where the switching or the CPU has to be scheduled like a preemptive way. That means where some process is running because of some event, this process will be taken away from the CPU and some other process has to be scheduled. Some other process has to be scheduled. So it is going to be preemptive. It means that the process has not completed its computation with the CPU. If you give in the time, if you offer the some more time, the process will continue its execution. The process will continue its execution, but it was stopped. It was stopped because it was taken from running to the ready state. So therefore, the process need to be scheduled. That means some other process need to be scheduled. And this is going to be preemptive scheduling. And likewise, the third one also. Suppose a process which is waiting and it joins the ready queue. If it joins the ready queue, and suppose the process is a high priority process or something, some other thing, then the scheduler will schedule this process center. Then the scheduler will switch the CPU from the current process to some other process center. So therefore, what I mean to say is that here, out of these four possibilities, the 1 and 4 will be viewed as a non-preemptive scheduling, and whereas 2 and 3 will come under the preemptive scheduling. Preemptive scheduling means actually here, even though the current process can execute or can compute further with the help of CPU, but still the scheduling has to be done because of some other event. It's not to be preemptive scheduling and all. Whereas a non-preemptive scheduling means the process is voluntarily leaving, so therefore the CPU has to be scheduled. So that way there are two types here, the preemptive and non-preemptive scheduling. And non-preemptive scheduling, there is no problem at all. There is no issue at all because the process currently running is voluntarily coming out of the CPU because of some event to occur or some IO is required to be fulfilled or whatever, or otherwise the process reaches to a last statement. So that way it's known to be non-preemptive scheduling and where there is no risk at all. But when you come to the preemptive scheduling, that means that the process is running. In middle, you are stopping. In middle, you are stopping. You are switching the CPU. Some process is running, and in the middle of execution, or in the process of in the middle of the execution, you are forcing the process to be stopped execution, and some other process will be given to the CPU and all. So this is known to be a preemptive scheduling, and there are some issues with the preemptive scheduling. That means some race conditions may arise. Race conditions means suppose a process right now is executing and those instructions are executing some shared data or they are modifying or they are accessing some shared data, shared variables and all. At that time, suppose if you switch the CPU like immediately, then there are chances of the data inconsistency or the problems may arise and all, right? That is at the user data or the user program when it's doing. And sometimes the kernel program or kernel routines are they are executing by CPU. And with the execution of kernel routine also, sometimes no, the preemption may occur. That means some signal, some other the interrupt may arrive. So at that time, the kernel routine, whatever kernel, the kernel program, it's also a program where the kernel routine is executing. In the middle of a kernel routine, suddenly this kernel routine is replaced with some other thing, whatever is demanded and all. So at that time also, because sometimes when the kernel, when the kernel system routine is doing, and it's modifying some data structure within a kernel and all, and if it is in the middle of that, and if you preempt that, then again there are chances of race conditions may occur and all. So there are different ways to avoid that. Basically, this race condition and all these things can be avoided by using appropriate the process synchronization techniques and all. And one of them will be like, for example, when you are axing either the kernel routine or the user routine, when you are axing certain instructions or certain shared data or shared variables and all. And at that time, you can able to stop the considering the interrupt and all. If any interrupt occurs and all, you can ignore that, or you can block the interrupt for a period of time where a kernel is performing some critical operations or a user data is performing some critical instructions it is executing. At that time, you can block the interrupts and all. You can block the interrupts, and that the interval that is you are blocking interrupt should be as minimum as possible, as small as possible. It should not be very long. Right? If it is very long, then there are problems, because even though the events are occurred, but those are not considered, they are simply ignored. So that will be a loss. Right? So these are the issues with the preemptive scheduling and all. Whereas non-preemptive scheduling, it's very straightforward. There is no issues at all. And the dispatcher is nothing but when you're switching the CPU from one process to other process, whatever the time that is involved in the switching process, that is known to be the dispatch latency. It's nothing but similar to the context switch and all. The same, not similar, it's exactly the same thing only. And here we'll say it's a dispatcher, because when you are removing a process, then again you need to identify that which process to be brought in to be scheduled next and all. And for that, actually, short-term scheduler has to decide that. And then we need to identify that, we have to brought that process status from the kernel, and then you have to place it in the appropriate CPU registers, everything has to be placed. Then you have to start the program and all. So all these time components that are involved in this process, in this switching, is known to be the dispatch latency and all. This is just similar to the context switching and all. And here our goal is that this dispatcher latency has to be optimized, has to be as minimum as possible, right? Then when you are scheduling the process to the CPU, so what is the criteria? What are the various parameters that need to be optimized? There are different constraints in which the scheduling has to be carried out. That depending on the applications. Like for example, CPU utilization. This is at most important. CPU. That means we need to make the CPU to be busy as far as possible. Like throughput, that is the number of processes to be completed in a unit time, has to be maximized. Turnaround time, it's a generic term, the amount of time that is required for a process to complete, like a process that enters into ready queue to the time that leaving the system at all, like a proper termination at all. It's not to be turnaround time. And the waiting time is nothing but the amount of time the process has been waited in the ready queue. Here in this context, we are just focusing on only CPU scheduling. Otherwise, the waiting time means it involves the waiting time that is associated with the IO queues also. Because the process, if you look at the process state diagram, the process visit different states, different resources and all. And one of the resources is CPU. And there are other resources like the keyboard and then the disk IO and so many other things are there. So strictly speaking, the wait time will be the sum of all those components of that wait time. But here in this process scheduling, we just focus on CPU scheduling. So therefore, the waiting time is nothing but the total time that is spent by the process in the ready queue is known to be wait. And the response time is nothing but the amount of time that is required, that's taken by a process. Like when your request is given to a CPU, right? When your request is given to a process, when you're giving a request and you expect response from the a process and all. Like it means that suppose you take some user interaction, like for example, you by using a web browser, then you are just browsing something, for example. So in that, giving a URL to that is nothing but you are giving a request, and then you expect that the response, the whatever the desired image or video, to be played immediately and all. So that is not to be responsive. That is the time interval between giving a request to a first response, whatever you are arriving, you will receive. So that is not to be a response time at all. It's not to be a response time. And mostly in case of interactive applications, this response time is very important. The response time is crucial, right? In case of interactive applications. Whereas non-interactive applications and all, response time doesn't matter at all, because there the user interaction and the inputs are not required at all. So at the beginning itself, whatever is required will, all the files, whatever we are passing to the, we are attached to the process and all. Then our ultimate goal is that actually the process has to be completed, that the turnaround time to be optimal, right? Turnaround time to be optimal. So that way, there are various applications where, in case of interactive applications, response time is a crucial one, and whereas in case of batch systems where where the user interaction is not required, in that case, the turnaround time or throughput is important. Yeah, these are the among those 5 things. So for optimal in view of optimization, like these are the things: maximization of CPU utilization throughput, and a minimization of the remaining parameters. These are the important. And and it's not that all the 5 parameters have to be optimized together and all. It cannot be. And depending on the application and all, we have to give different weightages to the different parameters. And now we'll just start the various scheduling algorithms. And here I'm not discuss these things and all, because they are very generic and all. And all of them were explained with the appropriate examples and very easy to follow, not anything to discuss here and all. And here the first algorithm was, or first scheduling method was first come first serve, or first in first out principle and all. First in first out scheduling algorithm. And here, assuming that there are 3 processes, all are available in the ready queue, and their times, that means their execution times that are required, will be like this is the order 24, 3, and 3. And since in the first come first served, if they arrive here in this order, P1, P2, P3, right? If they are all are available, and the order of arrival will be P1, P2, P3. As per the first come first served basis, if you schedule these processes to the CPU, and you can able to see that all these 3 processes will complete in 30 milliseconds or in 30 time units and all, right? And here, if you try to analyze the waiting time, and since all 3 processes are available from a particular time instant, but P1 is the sequence will be P1, P2, P3 follows. So for P1, the waiting time will be 0, right? And whereas for P2 and P3, even though they are also available, but they have to wait, because here the scheduling criteria will be first come first served. So first the P1 will be served, completed, and after that P2 and then P3. So that way, if you try to analyze the waiting time for each of the process, like they are 0, 24, 27 with respect to P1, P2, P3 respectively, and then the average wait time will be 17 milliseconds, right? And here the same thing, if you just change the order, instead of the first come first serve, suppose the processor arrived in this order, like P2, P3, P1, or P3, P2, P1, for example. So in this order, if you follow this, if you try to analyze the waiting time, or average waiting time, you can see that average waiting time will be reduced to 3. And here it means that in case of first come first served, the waiting time, or the average waiting time, that depending upon the order in which the processor scheduled and all, in which the processor scheduled. And here the reason for here having the less time, and the reason for that the more time will be because we are given allotted the process which requires the more computation time or a larger CPU burst time, that has been given first. So therefore, the other process are waiting. Other process are waiting till completion of that one. So because of that, the short process, the process which have the short computation time, so they need to wait for a long time. So in view of that, if you analyze the average waiting time and all, it is more. It depends upon the order in which the processes are scheduled and all. And this is known to be like a convoy effect and all. It means that if a shorter process are behind the long process, then all these short process has to wait till completion of this one, till completion of this one, right? So therefore, the average waiting time will be increased and all, right? So like you can see the example of like suppose if you take one CPU bound process and there are many IO bound process. IO bound process means a process which needs most of the time it will spend for taking the IO. So in that case, actually here in case of IO bound process, the CPU burst times are very small and they will spend a lot of time for IO. Whereas the CPU bound process means actually here, as I told you, the example like a process that consists of computation of a factorial or a computation of, for example, just computing the sum or computing some statistics and all, where they are like basically the data crunching and for that every time you need the CPU is required and all completely. So, like in case of CPU bound, one CPU bound process, there are lots of IO bound process where all these IO bound process have the where the small CPU burst will be there, whereas the like CPU bound process has the largest CPU burst. So in this case, we can able to experience that the waiting time for the overall waiting time will be very large because whenever the CPU bound process when it is executing, and by that time the IO complete and all these IO processes will be waiting for the CPU's turn. And once this is completed, then again this is their terms this is their turns are very small, then they will immediately execute it and afterwards they will go for IO completion of IO again they will come back and waiting for this larger CPU the larger CPU bound process to be complete. So if you look at here the first come first serve basis, if there is a variation in the like CPU burst and all, then you can able to experience that the waiting time will be very disproportionate. So in the context, so to overcome that, one solution will be like one of them will be where in the case of first come first serve, we have seen that the shorter CPU burst process, so they need to wait for a long time for completion of the larger burst CPU process and all. So in that case, actually instead of waiting for a larger burst to complete, instead if there is a process having a shorter CPU burst, they have been prioritized. They have been given a chance for a CPU to execute, and afterwards the process which requires a longer CPU burst and then they can be handled. So that was the concept of the shortest job first scheduling. So it means that among the process, whichever requires the less time, so that has been given first to the CPU for its execution and all, for its execution. So that way, if you look at here, you can see this example where process and these are the CPU times, and here the process 4 has the less time. So accordingly, as per the burst times, if you schedule the process, you can see that the waiting time will be somewhat small. Otherwise, actually, without this, if you go by like normal, like first come first served basis, like you can able to get a more waiting time because the process P4 has to be because the process P4 as per the sequence, this is in the last turn. So this for completion of this one, the waiting time of this one will be like 6 plus 8 plus 7 and all. So this is the waiting time for this. And whereas for other things and all, you can have for P1, it may not be, it will be 0. For P2, it will be 8. P3, it will be like 8 plus 7. So all these things will be like not 8 plus 7, like 8 plus 6. So this is the shortest job first. And this is for the example, right? And it's not that the process contains only one burst and all. The process contains several bursts. So if you want to schedule the process in reality, in practice, we need to check for the current CPU burst, what is its length? And based on the current CPU burst duration, the process will be scheduled and all. The process will be scheduled based on the current CPU burst. Like how do you know the current CPU burst? Right? How do you know the current CPU burst? Like we cannot know. We are not aware of that. Maybe that actually we can get an overall idea that the application programmer, when he writes the code, he may have some idea that what will be the nature of CPU burst of this particular process and all. Right? He may have some idea, but we don't know that actually what is the, because in the process there are lots of hundreds and thousands of CPU bursts will be there. And then we need to, when you're scheduling a process and all, so we need to worry about, or we have to see that what is the current CPU burst of the process which are there in the queue. And among them, whichever is having the lowest CPU burst, that has to be given, that has to be prioritized. So in the reality, if you want to implement the shortest job first and all, because we don't know the burst times a priori, so we have to estimate, right? We need to estimate the burst times. Suppose there are 10 processes that are ready for execution. And now we need to estimate the CPU burst, the current CPU burst of these 10 processes and all of this. And among these predicted 10 bursts, whichever has the smallest, and based on that, you need to sort the process and we have to give access to the CPU and all. So how do you like, for example, how do you estimate the CPU burst? How do you estimate the CPU burst? So for that, actually, for estimating the CPU burst, you can, for initial estimate and all, it may go wrong, but afterwards, by observing the history, you can able to predict. That means from the previous observations, you can able to predict the current CPU burst and all, right? So for that, you can use this exponential averaging. It means that you can see this relation tau of n plus 1 equals to alpha into tn plus 1 minus alpha into tau n. So here the tau refers to the estimated or the predicted values, and the t refers to the actual values. So what it means here, what this relation indicates here is that, so when you are predicting the n plus 1th CPU burst, that means right now you are in the nth time, and now you want to predict the CPU burst for the next n plus 1th time instant. So for predicting the n plus 1th CPU burst, the prediction we are relating that this prediction of this n plus 1th CPU burst, we are taking into the T of n, because the T of n is already observed, because the nth instant, so we may be predicted, but afterwards, whatever the CPU burst time or whatever the CPU burst time it has taken, so based on that, we can get the T of n. Excuse me. Hello. Sorry. So here we need to estimate the n plus 1th time CPU burst. So for that, actually what we are doing, we are taking the tau of n and T of n. T of n is nothing but the actual the actual CPU burst of the nth CPU burst, and the tau of n is nothing but, so before knowing this one, like this way we have predicted the nth CPU burst also. We have predicted nth CPU burst tau n. So this tau of n is nothing but the predicted nth CPU burst, and T of n is nothing but the observed CPU burst at nth instant. So it means that this is the, suppose for predicting the n plus 1th CPU burst, we are considering the recent value, the recent actual value, and the recent history. That means the tau of n. Again, this tau of n, if you want to see that, again, if you want to expand this further, this tau of n is observed or estimated from the previous n minus 1 values, right? So that way you can keep on expanding this one. And here the alpha is nothing but a weighting factor. So here for predicting the n plus 1 CPU burst, we are considering the actual value, the recent actual value, as well as the recent predicted value, right? So tau of n is the actual length of the nth CPU burst, and tau of n plus 1 is nothing but we want to predict the next CPU burst. That we have no idea. We have to predict that one, because you are now assuming that nth instants are over. At n plus 1th instant, you have several processes are there. So for every process, we need to compute tau of n plus 1. That we are predicting, and then from the predictions, whichever gives the whichever process has the lower one. So based on that, we order the queue. And the process having the least tau of n plus 1 has been given first chance, and afterwards the next, and so on. And for computing this tau of n plus 1, we are taking these two components: observed one, that is observed nth one, and then the predicted one. Here predicted means actually here this particular component appears to be like only one term, but actually this contains the history, because if you expand tau of n, again, this is nothing but T of n minus 1 plus tau of n minus 1. And again, tau of n minus 1, if you expand, you will get further. So likewise, this is nothing but history. This is nothing but history, whereas this is nothing but the actual one. So based on these two components, alpha and 1 minus alpha, by giving different values like 0 to 1, if you keep alpha equals to 0, it means that actually you are not considering the recent one. Just you are taking the history only. Based on that, you are predicting the next one. And suppose if you put alpha equals to 1, there is the other extreme. It means that you are not bothered about history at all. Whatever you observed in the previous instant, so the same thing you are proposing for, you are predicting for the next also. That's what when alpha equals to 1. And so therefore, the shortest job first, whatever we discussed earlier, it is a non-preemptive one, where that is just for the purpose of just for showing the sample, where we are assuming that we have 4 or 5 processes and the CPU burst times have been given. That is at one instance, right? But in the process execution, we have a sequence of bursts will be there. So for every burst, we should be aware of that, like which one among these in this particular time slot, whichever has the least burst, that has to be given first. So that way you can say that the preemptive version of shortest job first can be viewed as like a shortest remaining time first. Shortest remaining time first. So this is nothing but preemptive version. This also we'll see later and all. So just like, yeah, here this is kind of a prediction. You can see that this square, the signal here, the black plot. So this is the actual CPU burst times of a process. That means at a first instance, actually the CPU burst time equals to 6, and at the next time instance it is 4, and again 6, 4, and again the next instance it will be like 13, and again it continues 13, 13, and so on. So here the black one is the actual values, and the predicted ones is nothing but tau of j. These are the blue curve indicates the predicted ones. So initially we have no idea, no guess, no idea at all, no history at all. So therefore we just predict that as some 10 units and all. But the actual value is 6 only, right? By taking these, by knowing this one, now next time we'll predict less. We predict it as 8, right? But here the actual value is 4. So that means still less. So now the next time they will predict it less. Then afterwards again it will be high. So again it will increase. So likewise you can see that this is the predicted one and this is the actual one, right? And anyway, the predicted one just follows the trend of actual one, right? And so this way you can able to predict the CPU burst of in the next slot, and based on that you can able to carry out the scheduling. You can perform the scheduling. So this is the one whatever I discussed. When alpha equals to 0, it means that just see the formula. This is the previous formula, like this one. This is the expression and all. Like predicting the n plus 1 burst depends on the recent burst, whatever you observed, and the history. Why this is history? This one, if you look at here, if you look at the expansion, tau of n plus 1 equals to alpha into Tn plus 1 minus alpha into tau n. And here again, we are replacing that tau n. Again, it's nothing but alpha into Tn minus 1 plus something like that. So therefore, when you expand that, you can able to see that the successive terms are like the multiplication, like you can say alpha multiplied by 1 minus alpha, like 1 minus alpha whole power j, and so on. So if since alpha is in between 0 and 1, so these values, these weighting factors and all will be reduced further as you go on, like as you go on the history, like from recent history to the past one, as you go on far and far, then the weightage will be less. So that's why this is known to be exponential weightage, exponential averaging and all. It means that whatever the recent one, we are giving a more weight, and then the next recent one less weight than this one, and the next one less than this one. And so that is indicate that is given by this one, 1 minus alpha whole power j and all. 1 minus alpha whole power j. This j is nothing but at a jth, it's a previous jth instant, right? So that way you can able to predict the current burst, and based on that you can make a decision and all. Right? So this is using exponential averaging, you can able to predict the current CPU burst, and based on that you can able to schedule. Yeah. The next one is like the shortest remaining time first. So far, whatever we discussed, those are the non-preemptive process. Those are the non-preemptive scheduling. Even the shortest job first, and even the shortest remaining shortest the next CPU burst. All these things are like non-preemptive schemes. And this is known to be like here. Suppose we want to make that as a preemptive scheduling algorithm, and that scheduling algorithm can be viewed as shortest remaining time first. So it means that, assuming that suppose these are the four processes and their arrival times are 0, 1, 2, 3. It means at the time instant 0, when we want to schedule it, at that time only one process is available. Then after one time unit, then the P2 also joined the queue. Now the ready queue contains like P1 is already executing and P2 is also there. And that at the time instant 2, you have one more process joined. So likewise, so these are the arrival times, and these are the processes that are arrived at this time instant and all. And these are the corresponding burst times. These are the corresponding burst times. And now the shortest remaining time first, it's a preemptive algorithm. It means that, like for example, if a P1 at the time 0 instant, a P1 has been arrived. So the burst time of P1 is 8 units. It means that P1, in case of non-preemptive scheduling, at the time 0, only P1 is available. Now the P1 has been given access to the CPU, and a non-preemptive scheme, the P1 has to complete. P1 has to complete. That means P1, the 8 units has to be complete. Then only the next process will be given. And this is the shortest remaining time first. It's a preemptive algorithm, a preemptive scheduling. So where that means at time 0, only P1 is there. So you are giving access to the P1. And now the P1 is execution. The P1, the CPU is executing the P1 and all. At time 1, P2 has come. P2 has come. And now the P2 burst time is 4. The P2, the CPU burst time is 4, which is less than the P1's remaining time, because the P1 has started here, and at the end of one unit, the P1 completed one time unit. There are 7 time units are remaining in the P1 process. And at that time, the P2 has joined. The P2 has only the duration, only the burst duration is 4. So therefore, the P2's burst is smaller than the P1's remaining burst. So therefore, since it is a preemptive scheduling, and among these two, the P2 is the shortest job. So therefore, the P2 has been given chance. The P2 has been, that means the P1 will be switched off. That means the CPU is switched from P1 to P2. P1 to P2. And now the P2 is going on. P2 execution is going on. And at the time instant 2, the P3 has been arrived. P3 has been arrived, but its duration is 9. And the P1 duration is 7. So therefore, out of these three, P2 is the shortest job. So the P2 will continue. P2 will continue. And then come to the fourth one, at the time instant 3, at unit 3, the P4 has been joined. P4 has been joined, right? At 3, P4 has been joined. So by that time here, at this instant, P4 has joined. The P4 time is 5 units, and the P2 is executing. P2 already, the 2 units have been completed. Only the P2 has remaining 2 units are there. So therefore, P2 is the shorter one. Not only that, and so therefore the P2 will continue. P2 will continue. So the P2 completes now, because 4 units, it will complete here at the end of 5th unit and all, right, from the beginning. Then in the remaining 3 process, the P4 is the minimum. P4 has a minimum burst, right? Because the P4 has 5 and P3 has 9 and P1 has 7. P1 has 7. So therefore P4 will be given, right? So that way you can able to like schedule the process based on the shortest remaining time first. It means that here the scheduler will dynamically check whenever the new process joins into the queue, and it checks that whether the process duration or the process burst is smaller than the existing ones. If it is the smallest one, then immediately the process switch will take place. That means the existing process, whichever is running, it will stop, and this process will be given a chance. So that way, if you compute the average waiting time for this, in this case, you can see that it's about 6.5 milliseconds. 6.5 milliseconds, right? So this is a preemptive scheduling algorithm, whereas other ones, whatever we discussed, are non-preemptive scheduling algorithms, right? Okay. Then the priority scheduling means here the criteria is that somehow the process will be allotted some priority based on some based on its application or whatever and all, based on its whatever, some based on its nature and all, some priority has been given, and then among the priorities, whichever has the highest priority, so that will be given a chance and all. It's a very straightforward one. And we can say that the shortest job first can be viewed as a priority scheduling one way, where the whatever the the time interval, whatever is there, so based on that the priority will be decided. And among the CPU, among the process, whichever has the shortest burst, so that has been given the higher priority. So that has been given a chance for execution and all. So that way we can view the shortest job first, and also can be viewed as a priority scheduling, where here the priority is decided based on the burst time, based on the burst time. And again, here this priority scheduling also either preemptive, non-preemptive, right? This is depending upon the way you implement. You can see that preemptive, non-preemptive. Preemptive means whenever the new job arrives, at that time, it just check, the scheduler will check that, and then based on that, whether the current process to be preempted or not preempted. In case of non-preemptive, the current process will not be disturbed at all till it reaches to the end. Its completion of its either it terminates or it will go into wait state. Till that, the process will be continued. The CPU will execute that one, in case of non-preemptive. Whereas in case of preemptive, whenever there is a change in the priority in the queue, then immediately the process will be switched. That is the difference between preemptive, non-preemptive priority scheduling. And then here the problem with the priority scheduling will be this one: starvation. It means that the low priority process will never get chance to execute, because all the time a process having the moderate or high priority process are available. So till completion of those processes, the low priority process will not get a chance at all. Sometimes no, most of the times if the process are high priority, then the low priority will not get a chance, and then after a long time also they will not be executed at all. So this is known to be a starvation, and this can be avoided by using aging. Aging means actually somehow if you have to uplift these things, right? So you can consider the aging as the criteria. With that, the priority can be upgraded. Like for example, for every 10 milliseconds, the priority can be improved, can be increased, and also some at some point of a time, even though the lowest priority process also will become highest priority process. So that way, you can solve the problem of starving by using aging and all. It means that whatever the wait time was there, so with by based on the wait time, the priority will be enhanced and all, increased and all. At some point of a time, the process having the lowest priority will wait long time, and then it will give a higher priority and it will be executed. Okay, anyway, this is the example to this. And one more thing here, this is known to be like a Gantt chart, like the way the visualization of the scheduling of the process and all. You can see like on a time axis where the process will be mentioned and the time units will be specified over here. And so this is known to be Gantt chart and all, and with which you can able to analyze the scheduling the parameters and so on. And round robin, this is all of us are familiar and all. Here, in case of round robin, the idea here is that a process has been given a time quantum, and at the end of a time quantum, the process will be switched. Process will be switched, and this is a kind of the preemptive one, because this will come under the point two, like among these four ways of process switching. So this is the round robin is nothing but it's a point two, where a process will be shifted from running to the ready state, like when some event occurs. So here the event happens to be your timer interrupt and all. So in case of round robin, it's mostly it will be used mostly for interactive applications or interactive process and all, where the response time should be minimum or response time should be very, very less, so that the users can able to interact the progress of the programs and all. So here the process will be scheduled based on round robin, where each process has been given a time quantum, and then the time quantum will be it's reasonable enough where the response time will be we cannot perceive that response time. We'll feel that all the processes are running parallelly, kind of a thing. So here each process will given a time quantum, and then if a process in between before the time quantum itself it requires IO, it will be switched anyway. Otherwise, when the time quantum expires, then the timer interrupt will generate and then the process will be switched. And now here the issue is that what will be the time quantum? What is the value of the time quantum? Suppose if the time quantum is very small, for example, if the time quantum is very small, then what happens? Then the CPU will be most of the time, or CPU will encounter more switches and all. CPU will encounter more context switches because, for example, instead of 10 milliseconds, for example, if you perform a time quantum size equals to 1 millisecond, it means that for every millisecond you need to switch the process. It means that you have to perform the context switch or you have to perform the dispatch latency, whatever. So that will be the overhead will be increased if you give a very less time quantum and all, right? That is a problem, right? If your time quantum is large, if you keep the large time quantum to avoid this context switching, the problem is that the response time will be very poor, or it's nothing but it will be finally end up with first come first out basis. If the time quantum is sufficiently large, it means that it's nothing but first come first out basis, or FIFO principle. If the time quantum is very small, then the number of context switches will be more, and with that the overhead will be increased. Overhead will increase. So therefore, when you are choosing a time quantum, the time quantum should be such a way that the response time should be reasonable, and accordingly you have to choose the time quantum. And at the same time, because of the time quantum, the efficiency of the CPU should not be lowered. That means the number of context switches should be reasonable. It should not be very high. So this is the round robin scheduling algorithm where you can see that here the time quantum equals to 4 and these are the burst times, right? And this is the way the process will be scheduled and all, right? P1 because time quantum equals to 4 and then after the 4 time units, then the P2, P3 will be given. This time quantum, this is less than time quantum. Then afterwards the P1 will be scheduled, right? Yeah, right. This is the one. Like if you give a various time quantums, you can able to see that. Suppose if the time process time equals to 100, burst time equals to 10 units. If you keep various time quantums, you can see that how the context switches related to that. It's a simple illustration. It's a very simple intuition. Right. And then the time quantum also affects the turnaround time, and not only response time, even the turnaround time also. And here this particular plot shows that by varying the time quantum, how the turnaround time will be varying. And you can see that at a larger time quantum, the turnaround times will be stabilized here. Right. Okay, so and next one is a multi-level queue. So far we discussed about various CPU scheduling algorithms or scheduling methods where the CPU will be scheduled using single queue, and that queue will be maintained by with different scheduling algorithms, whether it may be first come first or the shortest job first or whatever, or the round robin or priority scheduling, whatever. But here, in general, normal realistic systems and all, present systems, they don't use the single queue. They use the multiple queues, and then they combine these queues in a very strategic way, and then the CPU will be scheduled as a result of these multiple queues and all. So we'll see the details of these multiple queues later and all, how they are implemented, and how the problems will be resolved having these multiple queues and all. So those things we'll discuss in the next lecture, Thursday. So mostly in Thursday, so whatever we can able to cover, so we'll cover till that point related to this CPU scheduling and all. Then afterwards we'll move on to the next topic like synchronization or whatever. And as you see, these whatever the topics I'm just referring, these are mostly the self-explanatory, or most of them are very intuitive things, which you will come across in various scenarios and all. But anyway, so we'll stop here. Okay. So let me stop the recording.